Intermittent visual servoing. Efficiently learning policies robust to instrument changes for high-precision surgical manipulation. Automation of surgical tasks using cable-driven robots is challenging due to backlash, hysteresis, and cable tension, and these issues are exacerbated as instruments are exchanged frequently and their properties change over time. In fact, each instrument is only permitted to be used for 10 operations regardless of the operation length due to potential instrument degradation, and even within this permitted use window, instruments frequently fail. Even for a single instrument, the cabling effects are inconsistent due to high pressure, high heat sterilization between patients, instrument collisions, and general wear and tear. Thus, developing policies that are efficiently transferable across instruments is critical to the automation of surgical tasks. The fundamentals of laparoscopic surgery peg transfer task involves transferring 6 blocks from the left pegs of a pegboard to the right pegs and then transferring them back. As each peg cylindrical is 2.25 millimeters wide and each block's opening has a 4.5 millimeter radius, the task requires high precision, making it a popular benchmark task for evaluating human surgeons. The board and blocks are both red to simulate the lack of color contrast in the human body. We propose a framework for automation of high-precision surgical tasks called Intermittent Visual Servoing, or IVS. IVS intermittently switches to a learned visual servo policy for high-precision segments of repetitive surgical tasks, while relying on a coarse open-loop policy for the segments where precision is not necessary. Flashes indicate images taken by an overhead camera, which are used once before each transfer to plan course trajectories and at a high frequency for visual servoing. We apply imitation learning to rapidly train a policy that maps top-down RGB images to small corrective motions. Using teleoperation, we collect demonstrations of small corrective trajectories for a surgical subtask. The policy uses a pre-processed image as input and regresses the corrective direction and classifies the completion status. The robot moves in the corrective direction until determination condition is met. Results on a Da Vinci research kit suggest that combining the coarse policy with half a second of corrections from the learned policy during each high-precision segment improves the success rate on the FLS peg transfer task from 73% to 99%, 31% to 99%, and 47% to 100% for 3 instruments with differing cable-related effects. To evaluate instrument transfer, we compare it to an uncalibrated baseline, which uses the default DVRK controller, and a state-of-the-art calibrated baseline, which uses a learned recurrent dynamics model to correct for positioning errors. For instrument A, after training on 180 corrective human demonstrations, IVS succeeds on 118 of 119 attempts. This is comparable to the performance of an expert human surgeon. Now, here's how the same IVS system trained on instrument A performs when the instrument is switched to instrument B. And here it is on instrument C. Thus, in the context we studied, IVS attains the highest published success rates for automated surgical peg transfer. We believe this is the first surgical arm policy robust to cabling effects, as it is significantly more reliable than previous techniques when instruments are changed.